Hey everyone, and welcome to this explainer. Today, we're going to dive into the absolutely fascinating story of how scientists took ordinary piles of metal and wire and literally taught them to learn and think like a human. I know, it sounds exactly like the start of a sci-fi movie where a robot suddenly wakes up, right? But honestly, the real-world story of how this technology evolved is even cooler, and we're going to break the whole thing down so it makes perfect sense to anyone.
I mean, think about it for a second. How can a computer, which, let's be honest, is basically just a really fast calculator that blindly follows instructions, actually learn from its own experiences to solve puzzles completely on its own? We all know computers are great at following rules, but how in the world do they go from just repeating lines of code to actually outsmarting human beings at their own games? Well, let's find out.
All right, let's kick things off with Section 1, Meet the Digital Brain. We are going all the way back to the 1943 breakthrough.
Picture this. It's 1943 at the University of Chicago. An American neurophysiologist named Warren McCulloch and a self-taught logician named Walter Pitts decided to team up. And together, they published this groundbreaking paper. Basically, they built on Alan Turing's ideas and created the very first mathematical model of a neural network. They proved that if you connect a bunch of really simple elements together, they could generate immense computing power.
So what did they actually invent to do this? They called it the artificial neuron. Now, to really understand this, I want you to visualize a bucket being filled with water. If you just pour a few drops in, nothing happens, right? It just sits there. But once you fill that bucket completely to the very top, it hits a threshold, tips over, and splashes all that water out at once. That is exactly how this artificial brain cell works. It waits and waits until it gets enough electrical energy to pass a certain limit, and then, splash, it fires a signal forward to the next cell.
And here is the real genius part. Because human brain cells act a lot like that tipping bucket, basically functioning as tiny on and off switches, McCulloch and Pitts realized that neural events could be perfectly translated into computer language. Think about it. If our brain cells are essentially just shouting yes or no, that a computer running entirely on ones and zeros can mimic that exact same behavior using simple math. This one brilliant idea is the spark that ignited everything we call deep learning today.
Moving right along to Section 2, How do machines learn? Supervised versus unsupervised learning.
Okay, imagine you have two different robots. The first robot learns through what we call supervised learning. This is kind of like you sitting in a classroom. You have a teacher standing over your shoulder, pointing out your mistakes so you can adjust your work until you get the right answer. The second robot, though, learns unsupervised. There's absolutely no teacher. It gets dropped into a massive pile of scattered blocks and has to use its own logic to sort them out, maybe grouping them by color or shape, finding hidden patterns entirely on its own.
Which brings us to Section 3, Playing Games to Learn. We're going to look at the 1952 checkers champion.
So in 1952, a researcher named Arthur Samuel wrote his very first checkers playing program for this massive, room-sized IBM 701 computer. Now, you might be wondering, why checkers? Why not chess or some super complex real-world math problem? Well, checkers has really simple rules, making it the perfect sandbox. It allowed Samuel to stop worrying about complex game mechanics and focus purely on teaching the machine how to learn from its past mistakes. To pull this off, Samuel used a super clever trick called iterative deepening. Let's visualize this happening right in front of us. Step 1, the computer looks at the current board and imagines glowing branches stretching out into the future, showing every single possible next move. Step 2, it basically acts like a teacher, stamping a number grade onto every possible future board setup based on how good it is. And step 3, it uses a mathematical process called minimax to travel down the branch with the highest winning score. It's literally like mapping out an entire maze in your head before taking a single step. But here is the absolute game changer. Samuel didn't just give the computer strict, rigid rules to follow. No, he let it learn continuously from the outcomes of its past games. The program acted like a real student. It started noticing which moves led to winning and which ones led to losing, and it gradually modified its own strategy over time. It quite literally taught itself how to become a master player. Let's jump over to Section 4, the nearest neighbor trick. We'll be looking at the KNN algorithm. So the K and nearest neighbors, or KNN algorithm, is another amazing supervised learning method used to classify things. And honestly, it works exactly like asking your best friends for advice. Imagine the computer stumbles across a completely mystery object. It immediately looks at the K closest examples right next to it.
K is just whatever number you happen to pick. So if K is 3, the computer literally looks at its 3 closest data points and asks them, hey, what do you guys? So how does it actually make the final decision? It just takes a vote. Picture a tiny voting booth inside the computer. If our mystery object is surrounded by 2 neighbors that are colored red and only one that is colored blue, well, the majority wins. The new object gets instantly labeled red. The beauty of this is that the computer holds off on doing any complicated math until the exact moment it needs to make a decision. It's incredibly simple, but incredibly effective at organizing the world around it.
All right, that brings us to Section 5, the AI time machine. Let's do a quick history of machine learning.
You know, the evolution of the digital brain started way, way earlier than most people think. Just look at this timeline. Way back in 1843, Ada Lovelace realized that machines could process symbols, not just numbers. Fast forward 100 years to 1943, and we get McCulloch and Pitts' artificial neuron, that tipping bucket we talked about. By 1950, Alan Turing was proposing a true learning machine, which led right into Arthur Samuel's 1952 checkers program. All of these continuous compounding breakthroughs built the solid foundation for 2016 when Google's AlphaGo did the unthinkable and defeated a human world champion in one of the most complex board games on Earth.
As we've seen throughout this explainer, the digital brain has evolved at an incredibly fast pace. From the simple all-or-none splashing bucket logic of an artificial neuron to mastering deeply complex games entirely on its own, the journey is truly staggering. Which leaves us with one big, exciting question to ponder. If a machine could teach itself to play checkers way back in 1952, what impossible problem will it learn to solve next? Thank you so much for exploring this amazing journey with me. Keep asking questions and keep learning.